So today is the last day that we're going to be working on Chapter 7, Section 2. We'll be moving on to Section 3 tomorrow. So simplifying radicals with powers under the radical sign. This first part is just notes. You can print these off. They'll be on the PDF, or you could go ahead and write them out. I'm just going to be, like I said, it's on the PDF. I'm just going to be talking about this and making little marks on this, but not much. Simplifying radicals with powers under the radical sign. So to find the root of a variable raised to a power, divide the exponent under the radical sign by the root, the index, and the result is the exponent of your answer. What in the world is that saying? Well, remember, over here I have a power 2. I have squared. Anything that doesn't have anything marked, we know that that's squared. And so, well, let's see, find the root of a variable raised to a power, divide the exponent, so divide 2 by 2, and then my, so the exponent is 2 divided by 2 is 1. 4 divided by 2 is 2. 6 divided by 2 is 3. 3 divided by 3 is 1. 6 divided by 3 is 2. 9 divided by 3 is 3. That's how I reduce these when I'm using these radicals and exponents. 4 divided by 4 is 1. 8 divided by 4 is 2. 12 divided by 4 is 3. So my new power is the exponent divided by the radical. A variable power is a perfect square if its exponent is a multiple of 2. A variable power is a perfect cube if its exponent is a multiple of 3. A variable power is a perfect fourth if the exponent is a multiple of 4. What in the world does that mean? X squared, 2, is a multiple of 2, so that's a perfect square power. 4, x to the fourth, 4 is a multiple of 2, so that's a perfect square power. X to the sixth, that's a multiple of 2, so that is a perfect square power. But x to the sixth is also a multiple of 3, so if it's a perfect cube power, 12 is a multiple of 4 and a multiple of 3 and a multiple of 2, so 12 is a perfect fourth power. It's also a perfect cube power and a perfect squared power. How does this work? What do I use these for? Let's look at a couple examples. So this is the steps that I'm going to follow. To simplify a radical with a power under the radical sign, first, factor into perfect squares, cubes, etc. Simplify by putting the root of the perfect square, cube, etc. outside the radical sign, leaving the non-perfect square, cube, etc. under the radical sign. So example, this here is x, the square root of x to the fifth. Okay, well, 5, pause for station identification. So let's see. 5 divided by 2. 2 goes into 5 twice. 2 times 2 is 4. 5 minus 4 is 1. So what does that mean? That means I have my square root. I'm going to have things outside my square root and things inside my square root. I have x squared outside my square root because that's what I divided 2 into. And I have a 1 left, so an x to the 1 stays inside the square root. Why? How does this work? Well, think about this. I'm taking the square root of x to the fifth power. So that's x times itself 5 times. Since it's a square root, I want pairs. There's 1 pair, there's 2 pairs. Just like I had my 2 up here. But there are 2 pairs. There's 4 x's altogether, but there's 2 pairs. So each pair brings out 1x, so that's x squared for the 2 pairs. What's left on the inside? The inside is this x, so that stays under the radical sign, and I have x squared times the square root of x. That is my answer. That's the reduction of square root of x to the fifth. Let's look at number 2. Number 2, I want x cubed. I want to take the cube root of these. So I have my cube radical sign. Any perfect cubes or anything that are multiples of 3 needs to come out, and anything that's left over stays inside. So 27, I'm going to move this down. 27 can be thought of as 3 cubed. X to the fourth can be thought of x to the third times x to the first. Y to the sixth is x to the third times y to the, y to the third times y to the third. Z to the fifth is z to the third, z to the second. Now, my expectation is not that you will do this, but I'm showing you what you're doing. Every group of 3 comes out once. So 3 cubed comes out as 1, 3, because the cube root of a cube is just 3. X cubed, this x cubed with the cube root of 3 comes out as an x. This x to the first stays inside my square root because there aren't 3 of them. Let's look at my y's. I have a y cubed and a y cubed. There are 2 sets of 3, so that's 2 y's, or y squared comes out. That's all my y's, so there's nothing that stays inside my cube root. Z to the third, that comes out as a plain z when I take the cube root, but I'm left with a z squared on the inside. So what did I do here? Well, again, this is my answer, first of all. 3 to the third power, you take the power, divide by the root. 3 divided by 3 is 1, so I take out a 3 to the 1. X to the fourth, 4 divided by 3 is 1, remainder 1, so I had an x outside the cube root, an x inside the cube root. Y to the sixth, 6 divided by 3 is 2, so it's a y squared without a remainder, so there's no y over here. And lastly is z to the fifth. 5 divided by 3 is 1, so I get z to the 1 with a remainder of 2, so I have z to the second stuffed inside. That's how I work these problems. So let's scroll down and look some more. Down here is the shortcut, and I said it's exactly what I did. Divide the exponent by the root to get a whole number and a remainder. The whole number is the exponent that goes outside the radical sign. The remainder is the exponent that stays under the radical sign. Let's try a couple others. I have a fourth root. 32 is 2 to the fifth power. X, y to the fifth power, z to the ninth power. I'm taking the fourth root of all of this. So I'm going to have a I'm going to have a fourth root. I'm going to have things outside and things inside or under the root. 2 to the fifth power. So like I said, you take the exponent, divide by the root. 5 divided by 4 is 1, so I get 2 to the first, but that has a remainder of 1, so a 2 stays inside. X, the power is 1. 1 divided by 4. I can't divide 1 by 4 and get whole numbers, so that x to the 1 stays inside. No x's come out. Y, 5 divided by 4 is 1, so I can pull out a y. I have a remainder of 1 because 5 minus 4 is 1, so y stays inside as well. Z to the ninth, well, 9 divided by 4 is 2, so this is z squared with a remainder of 1, so that's z inside the fourth root. One more time how I did this. I'm going to walk through it, dividing everything out. If I looked at this the way I did number 2, the first part, I want to put things in groups of 4s. I'm doing 2 different ways. The first way I showed here is the division way. The second way I'm going to do this is breaking things into groups of 4. First of all, I want the fourth root of, I'll move this down further out of my way. Oop, can't do that. Okay, I'll be all right. Well, this is 2 to the 5th, which is 32, 2 to the 5th. So that's 2 to the 4th, a group of 4. 2 to the 1st is what's left over. X to the 1st. Well, there is no group of 4, so it's just an X. Y to the 5th is Y to the 4th, and with one Y to the 1st left over. Z to the 9th is Z to the 4th, Z to the 4th, two groups of 4, with one Z left over. 4 plus 4 plus 1 is 9. So that's breaking it up into groups of 4. So now anything that's a group of 4, 2 to the 4th, Y to the 4th, and then I have 2Z to the 4ths have to come out. So the 2 to the 4th just becomes 1, 2. The Y to the 4th becomes 1, Y. Z to the 4th is there twice, so that's Z squared. And then I have my fourth root. What's left inside is use a different color. What's left inside is a 2, an X, a Y to the 1st, a Z to the 1st. There is my final answer. If you notice, they're exactly the same answer. It's two different ways to do the same problem. Which way do I care that you do? I don't, as long as you figure out one way and use that way. Let me scoot some of this stuff over. Oh, well. Number 4. Let's look at problem number 4. I'm going to go ahead and move this to a different page. So I'm going to bring up my little camera. Number 4, so I have more room. We're going to go to a different page. There's number 4, big and bold and beautiful. I have cube roots. I have a cube root here and a cube root here. I can combine that into one big cube root. I have 9 times 9, x to the 5th times x to the 3rd, y to the 2nd times y to the 4th, z times z to the 3rd. Combine like terms. 9 times 9 is 81. X to the 5th times x to the 3rd is x to the 5 plus 3, so x to the 8th. Y to the 2nd times y to the 4th is y to the 2 plus 4, so y to the 6th. Z to the 1st times z to the 3rd is z to the 1 plus 3, so z to the 4th. 81 is actually 3 to the 4th power, because 3 times 3 is 9, times 3 is 27, times 3 is 81. So now I need to do my cube root, and let's actually take the cube root of everything. So I'm going to have my cube root symbol. I'm going to have things that are outside my cube root symbol, and I'm going to have things that are inside my cube root symbol. 3 to the 4th, 4 divided by 3 is 1, so I can pull out a 3. 4 minus 3 is 1, so I have 1, 3 left over. My remainder is 1. X, 8 divided by 3 is 2, so this is 8 squared. Well, 3 times 2 is 6. 8 minus 6 is 2, so I have a remainder of x squared. Y to the 6th, 6 divided by 3 is 2. It goes in evenly, so I get y squared with no remainder, so there's no y under the cube root, Z to the 4th, 4 divided by 3 is 1, so this is z to the 1st, or just z. 4 minus 3 is 1, so my remainder is just z1, or z. So my answer is 3x squared y squared z, the cube root of 3x squared z. Anything that's a group of 3 can come out of a cube root. Anything that's a group of 4 can come out of a fourth root. Anything that's a square, so I can pull out any pairs out of a square root. That's how these problems look. That's how they work. This is my final answer. Hey, how much time do we have left? What do you know? 15 minutes. That's all the notes. Have a good day.